So you are all welcome back to our monthly meeting. That's a FANORG research group. As we said, we usually call upon researchers that are well known all over the globe to give us some talk. And this month, we are privileged to have Dr. Salawu. Dr. Salawu is a young researcher that have made a lot of impact. As a matter of fact, he was just recently listed among the top 2% researchers in the world. The ranking by Stanford University. He has over about 150 publications that are indexed in Scopus and over 1,900 citations. So, and that's why we call on him to make his presentation. Actually, we started before, but due to some disruption, we are now here to conclude. So, Dr. Salawu, you are welcome. Please, you can, we now
Okay,
use the
thank
floor
you.
so that you can conclude your lectures.
Okay, thank you. I'm also sorry for the disruptions in the connection.
You're welcome.
So we still on the method of solutions. So a final difference method has been used to solve the problems, and this method was chosen because there are other methods too that can be considered for solving the problem, but this one was chosen due to its accuracy, convergency, and stability. So, and this is the crystallization of the energies and the boundary conditions. So we have, so from the certain time when the gamma here is the Frank-Kamenetz term upon 0.7, and when it is 0.30, the temperature at maximum increases far better than when it is 0.07. So we consider the three cases of chemical kinetics. The 0.5 here talks about the bimolecular chemical kinetics. It talks about the arena chemical kinetics, and minor 2 here talks about the sensitized chemical kinetics. So the three cases of chemical kinetics was being considered under with different time, and we also have that there is increase of when gamma is 0.3 compared to when it is 0.07, and this is a good one. So that shows that when considering a Perovskite solar system and for a reactive system, then it is better to increase the gamma so that you can have more higher temperature than expected, because a solar system has to do with more energy conservations and I mean heat absorption, that is thermal heat absorptions and convection for you. So these are graphical results being considered. We look at the effect of Brickman. The effect of Brickman is the first graph here. Then that is the effect of Brickman was checked on the temperature, and it was discovered as the Brickman number increases, the temperature of the system, the heat that is being generated and transferred within the system also increases. And by implication, this is expected because, and this is a wonderful one. So when constructing or when developing a solar system, it is very important to take attention of the Brickman, because as it's increasing, the temperature is also increasing. Also here, we also check the effect of radiation. Sorry, this third, I did not put it in order. This third one here also talks about the effect of radiation on the nano material, on the hybridized thermofluid material for Perovskite solar system. So we also discovered that we increasing the radiation, that is the more the solar cell absorbing heat, then the more the energy that is being supplied. Also, we also look at the effect of ATMA on the flow velocity and the effect of Williamson term on the fluid flow. That is what is here on this particular one. This is very, very good because this is one of the things that is very important here. Because in the system, with the essence of considering magnetic and this physical material that is non-inhuman material is to drag down the flow. Because we are so much, when the flow is dragged down, then the heat within the system can be improved. So that's why we actually consider magnetic term and the physical material. The essence of it is to increase the viscosity of the fluid so that the flow rates of the fluid can be dragged down. Then we can have a better energy or better heat transfer. So that is also, we also check the thermal stability of the system. So this gives the thermal stability of the system. So at this region, this is unstable region of the system, and here we have the stable region. And at this point is this transition point. I mean the turning point. This is a turning point, and the same thing applicable here. So for this particular one, we check the effect of Brickman. Brickman was checked, and here we check the radiation term to check the stability of the system. And with this is more stable. And also this is as well stable, because anything above this turning point can lead up to blow up of the whole system. So in that case, even when we are so much interested in increasing the heat transfer in a system, we have to be conscious, because even if the heat is, we needed heat, but at the same time, there is a limit even to the heat we are interested in. If the heat is so much again, the whole system will collapse. So with this, this shows that the system can be stable and the thermal temperature is also stable. So that's why we can have a turning point, because anything above this region, there will be blow up. And with this, as the system, as the heat increases to this level, you make a turn. So, and that makes the system to be stable, and we will not experience a breakdown or blow up of the thermal system. So we also check the effects of parameter on Frank-Kamianski term was also, so we plotted here for these two graphs. For this particular graph, Frank-Kamianski term was plotted against artificial energy. So we now check the variation in lambda. So variation in lambda was checked, and also here the maximum temperature criticality is examined here against the artificial energy with variation in radiation. So with variation in radiation, we discover that the system reduces. The system reduces while the variation in lambda increase the system. And these are the outcome of this, the summary of the outcome of the study. The Williamson material terms and magnetic terms encouraged molecular bonding and physical viscosity, leading to a drag in the flow velocity as reported in the graph. Artificial energy does not directly influence the heat distribution. So what we also discovered that, because we consider an exothermic reaction, and it was observed that artificial energy does not in any way influence the heat distribution or the heat generated in that system. But what it does was just to stimulate reaction, just to stimulate the reaction, because nanomaterial. So as the heat is being absorbed, but so it stimulates the reaction in the system. That's just what artificial energy does. But it does not in any way affect the heat distribution as obtained from the study. Then the thermal propagation of the perovskite power generation is encouraged by Brickman number, radiation, and Frank-Kamianski term. So increasing in hot distance also increase the power generation, because heat distribution is increased. And also, just as I said, to avoid blow up, those terms, the Brickman number, the radiations, and the Frank-Kamianski term must be monitored to avoid a blow up in the thermal system. And criticality also, the last one, the criticality is raised at the unstable thermal region, but damp at the stable thermal region. So that makes the system to be stable. So this study will assist thermal power engineers in predicting their activity and protecting against unsafe conditions. Hence, extending the investigation to other photovoltaic solar energies and nanofluid is in a concentric cylinder is encouraged. So for further study on this particular research, other non-neutrino material can be considered. And for this particular one, we consider a channel. A cylinder can be as well be considered for the exothermic reaction of the nanofluid for solar cell for thermal generation. Thank you. Thank you.
Thank you very much, Dr. Salawu.
Please, before I leave the mic for you, please, I want to recognize, because I'm the participant, I can see some of my boss, which I need to acknowledge, but I could not see them early. I can see Dr. Bolaniwa earlier, was my boss, and I can see Professor Promise of the National Open University of Mathematical Center, Nigeria. I really recognize you, and many other persons that will not say few here. Please, I recognize you and every other participant. Thank you so much.
Thank you very much.
So over to you.
Yes, thank you, Dr. Salawu. Actually, I was also waiting to acknowledge the presence of our boss, the director of National Mathematical Center, Abuja, Prof. Promise. Mebine is a privilege. Is for all that I know about him, is highly someone that is very interested whenever research is happening, whenever conference is happening, anything about mathematics, he's at the heartbeat of it. He's always there. So, Prof. Mebine, we are glad for joining us, and it's a privilege that you are here with us. So, I don't know if...
Thank you so much for the program. Thank you so much for the program. It's a very good one. I think we need to do more of it. Thank you so much.
Thank you, Prof.
Thank you.
We are very glad for your passion about research. In fact, there's virtually no conference in mathematics that you don't attend. But if you are not just attending, you participate fully. Everything about mathematics, you are passionate about it. And we wonder whether we can do half of what you are doing when we get to at least your your proposition, sir. We are glad, sir, for the passion you have for mathematics, sir. Thank you very much. So we are glad to have Dr. Salawu present to us. As we said, Dr. Salawu is a well-known researcher. He has about 150 papers in Scopus, and recently he was listed among the top 2% researchers in the world. And so it's quite a privilege having him make this presentation. We want to find out if you have any question. Please, if you have any question, Dr. Salawu is here. You just unmute yourself and then ask your question so that we can take the question and the answers, and then we'll round up. If you have any question, you may indicate by raising up your hand, or just unmute yourself and then ask so that Dr. Salawu will respond, and then we'll round up. Yeah, Dr. Abimbola is raising up his hand, so you can ask. Dr. Abimbola, please, your question.
Yeah, thank you very much, Dr. Keke, for this kind of initiative. It's a very good one. And we are really enjoying you. I was with you last month.
Okay.
With the presenter, and here again, I'm here. So I want to appreciate the presenter too. I tried to follow him, and I think it was a very good one. So the only question I just want to ask, during his presentation, there are two areas. I think when Then I was not seeing my screen. I was just listening that time. When he was talking about one parameter in the Navier-Stokes equation, he said one constant or coefficient can be constant or can be variable. So I want to know which one did he consider in his own. That is first question. What about because I think you will remember. Okay. So I want to know which one do you consider. Then maybe the case of variable coefficient can be used for when you are considering the case of anisotropic, which is the usual one. I mean, when you consider the physical experiment.
Oh, it's even Dr. Okeke that is calling.
Yes, go ahead. Sorry.
Sorry, I'm with you.
Okay, thank you.
Okay, so
that's my first question.
Equation. So
yes, let me take the second question, sir.
Navier-Stokes equation considered a constant viscosity. And in most cases, viscosities are not always constant. In fact, most of the industrial material used now, they are not a constant viscosity. So there are some cases we consider a variable viscosity that is temperature dependent and things like that. And in their own, they consider Navier-Stokes actually focused on a non-Newtonian fluid. So for us to bring in, we consider a Newtonian fluid in this particular. So we assume that the viscosity there is non-Newtonian in nature. That is a kind of a viscoelastic material. Okay. But the major one from Navier-Stokes actually focus on a non-Newtonian, but for this particular study, we consider a Newtonian. But we also assume, because a non-Newtonian actually has viscosity that is not constant. So that's what we did.
Okay, thank you. Yeah. Yes, sir. Then the second question, very briefly. Yes, when you were presenting, you were giving some parameters and their value. So you said that they are experimental, that you did not just fix them. So I just want to ask, what's results of the experiment? Do you have any what do I put now? Any value apart from this theoretical, so I will say results? Do you have any model that can be used in industry, or do you have collaboration, or you are planning to have collaboration to what will make this work to be translated to what it can be used for industrial purpose?
Okay, that's a wonderful questions. The value that was used, their experimental value and their standard. So for those materials, those are their basic properties and their standard values. So those are the value that was used. Though for this particular study, the model is a standard one and it's real, and it can be applicable in industry and in engineering and many other science and engineering activities or nanotechnology area. Though this work is not yet in collaboration with any industry or things like that, but I look forward to have such opportunity for industrial collaboration. Hoping to have one. Thank you.
Okay. Yeah. Thank you, sir.
Thank you very much, Dr. Abimbola, and thank you very much, Dr. Salawu. And we want to have the next person, SOA. SOA, you are raising up your hand. You can unmute yourself and ask your question. SOA, that's the name you have in your Zoom here. Yes. SOA, please ask your question. You are raising up your hand. Yes, you can ask.
Okay, thank you. My name is Professor Samuel Adesoya from Redeemer.
Thank you, sir. Thank you, Prof, sir, for joining us, sir.
My question is on the model equation. If it can be displayed again.
Okay.
The mathematical formulation, the equation, the dimensionless equation. The equation in dimensional form.
Okay, I don't know if Dr. Salawu can display that slide.
Okay.
In dimensional form.
Yes, yes, the original equation.
Yes. Here you have it. That is
No,
it.
this is dimension.
Original equation.
Okay. Yes, yes, yes. Because I had the now my question is on this gamma radiation. Hello, sir.
Yes, I'm with you.
It's listening, Prof.
Hello.
Yes, it's listening, Prof. We are with you, sir. Proceed with your question.
That's your the Q dy, the equation 6.
Yes.
That the Q dy, that gamma radiation, did you linearize it?
Yes. It was also transformed. There is an approach. It was not just linearized.
That is my question. Why is it linear?
Very well, so that I can respond appropriately.
Okay. Because what is the expression you use for the Q dy?
Okay. Yeah.
Oh, okay. Okay, that is raised to power 4.
Yes.
All right. I thought you linearize it. That's why I'm a bit worried, because if you try to linearize it, then there will be a problem because of the because of the Frank Kanemaristy constant, the radiation reaction time there. It not balanced.
It's okay.
I thought you try to linearize it. No, I've seen it. Am I speaking with Dr. Salawu?
Thank you.
Yes.
Is that Dr. Salawu?
Yes.
Dr.
Yes.
Salawu? Oh,
yes, I'm
Professor.
with you.
Yeah,
Professor.
It's listening, Prof.
My boss. Sorry, I could not, because of the name you use. I recognize you, sir.
If that is
I can't hear him again.
Thank you, Prof. I think your question have been taken care of. Thank you very much.
Yes, yes.
Thank you, Dr. Salawu. Mr. Danladi is asking if we can provide the materials. Yes, I have the slide of the presentation of Dr. Salawu.
That's just that.
So I will share it. I will share it to different platforms, NMS, and all other platforms. So you will get it. In all the platforms for mathematics, I will share it. So you will get his presentation. Thank you very much, Prof. SOA for that question. We want to find out if we have any other questions so that we can round up. Any other question? You can just unmute yourself to ask if you have. Just one question more, then we are done. Just one more question. You just unmute yourself, then you ask your question, if you have any. Okay. I think Dr. Salawu have actually done justice to the topic, and it was an exciting time with him. And I want to believe that many of us, especially young researchers, because that's the essence of this meeting, to develop interest in all these areas and then see how others did it. Those that have done it, those are the people we invite, and we learn from them and then see how we can do it. So I want to use this opportunity to thank Dr. Salawu for honoring us, to share his experience and his research activities. We are glad at FANORG and the entire Nigerian Mathematical Society and community in Nigeria and Africa. We are glad. So we want to thank you for joining us and accepting our invitation to present. For us in FANORG, we usually have our monthly meeting. So this just the October 2024 series. By next month, we have another guest that will be talking to us in another topic. So on behalf of FANORG Research Group, I want to appreciate all our participants, all those that have joined us. I want to thank you very much for your time. Thank you for your patience. May God bless you. The meeting have come to an end now, so we can.
Thank you, sir.
Yes.